Done that once or twice.
Yeah. We'll do a full 90-minute episode on religion and philosophy in
Yes.
Fantastic.
part 3 of Quantumania. So get yourselves
my
ready for
niche,
that.
guys. This is my niche.
Welcome to Cloud Realities, an original podcast from Capgemini. And this week, we are checking back in with our colleagues at Google Quantum AI and getting an update on what's gone on since the last big episode we did on quantum called Quantumania last year. I'm Dave Chapman.
I'm Esmee van Giezen.
And I'm Rob Kerner.
And I am delighted to say that rejoining us for this episode is Catherine Vollgraff Heidweiller, the product manager at Google Quantum AI. And also rejoining us, actually, because James joined us when we were at Google Next very recently. We've got James Goeders, who's head of product at Google Quantum AI. Catherine, James, good to see you. How are you?
Great to see you. Very well.
Hello.
How are you?
Thanks for having us.
Oh, welcome back, both of you. It's great to see you. And James, I believe it is very early on a Friday morning where you are.
Too early.
It is. It's early here in Santa Barbara, California, but I'm excited to talk with both of you, or all three of you, this morning.
Well, thank you so much for making it at such an ungodly hour. It's much appreciated. And Catherine, I believe you're in London?
Yes. It's nearly weekend here. I'm looking forward to what's next.
Yeah, very good. Very good. And obviously, Ez and Rob are here. How are you guys? You good?
I'm fine, David. It's Friday, completely blue skies, rather strange for where we are, and I'm looking forward to enjoying the weekend. So moods and spirits are high.
Yes,
Very
definitely.
high.
I have the same, and it's actually been full moon, so I'm still on the same high energy.
Oh, do you get energy from a full moon?
That we've had this. I think she's secretly a werewolf. That's what we've just discovered, isn't it?
Yeah.
I mean, that is literally it. You basically just declared on
It's
the
not
podcast
secretly.
a full moon gives you energy. That basically makes you a werewolf.
Yep.
Yep.
And she's not. Well, there you go.
I'm not even
on
gonna.
that bombshell.
Yep.
I'm embracing it.
Why not? What's confusing you this week, Rob?
Right, David. This week, education has a bit of a problem, and it's not sure how to tackle it.
It's got more than one, hasn't it?
Well, yeah, but AI students are rather inventive and creative, and they're finding a way to get round things, and they're starting to struggle with students using AI for coursework, in lectures, all sorts of stuff, right? Because obviously you've got a tool out there. It's very, very powerful. We've seen a massive advances around it. And so all the coursework basically a lot of AI is being used in the coursework. It's homogenizing it. It's not properly testing the individual. So what they're doing is they're wondering how to fix that. So they're moving back to more of an exam-based system. So put them in a room, no technology, with a pencil, off you go, answer the question, right? But for certain people, coursework is much better because it proves them in a different way than those who may struggle with exams. And so the education balance and what's going on is, how do we deal with students using AI but actually proving that they've got a capability to be able to give them a certification to say you're good at X, Y, Z, 1, 2, 3. And I'm confused about where education's going to go, because actually if you continue to use AI in education like it is, and it's being abused by the students, then you're not properly educating them. They're finding an easy path, and that easy path may not prove their capability.
This is a show in its own right. But I've been thinking about this quite a bit, actually, because I've got kids who are 13 and 15 going through the education process. Like, what would it make sense that they did? Now, I don't know whether you remember, we had Dave Snowden on the show. We've had him on a couple of times, but he was...
Who could forget those episodes, David?
They're dense, that's for sure.
they are difficult episodes to comprehend, but yes.
But he made the observation about AI in education, which I think is happening in the US, James. You may or may not have clocked this, but I understand that a number of the high-ranking schools are removing computers and information machines from the classroom because they're focusing their teaching on human critical thought and what it's going to mean to be a human in the intelligence age. It is like how you differentiate, because retaining information, regurgitating information is no longer going to be a competitive skill, because AI machines are going to be able to do that far faster and more effectively probably than humans. So it seems to me that the education I think I've never been a huge fan of highly vocationalized education. So my sort of cod take on it is the major sort of bedrock classical subjects, the sort of sciences, things like maths and basic languages and stuff like philosophy and history, just taught in a classical way, which is teaching problem solving, looking at human patterns, looking at human behavior, all of those sorts of things. I don't think they're ever going to not be relevant. And I've seen recently a few little things pop up on things like, Instagram reels and things like that of sort of people talking about this exact subject and saying stuff like, those are the sort of subjects that people should focus on. So that's sort of where my head's at. The other thing that occurred to me as you were talking through was, are you just making a similar sort of complaint, albeit far broader than the introduction of calculators into mathematics?
But this is the thing, right? So education understood then the calculator was a valuable tool. They were ubiquitous. It integrated it into the system. So is it, and this is part of the confusion, is it that education needs to modernize itself for the new tools that present themselves to us, as opposed to raging against the machine and saying that tool is unfair, you shouldn't be using it, go away? And is it the old guard not becoming, just not accepting that this tool that is new to us is here to stay and it's not going away, so we better integrate it?
I think it's time to make that shift, because who's deciding what kids should be learning? And I think in history, a lot of the educational systems were the ones deciding these are the talents and these are the skills that they need. But I think it should be completely the other way around these days.
Well, I was at a recent school event for my 13-year-old and looking at kind of options that they were going to take. And so obviously we went through and had a look at each of the curriculums, and the computer science curriculum had stuff like Python on it. It's like, I mean, really, it's like, that's going to be outmoded. You're just not going to need that as a skill.
But if you take a programming language, the concept of choice, iteration, and sequence, the three bedrocks of programming, that's a powerful. I'm just sorry. The system just decided to do a thumbs down for me on the camera. Anyway, but those concepts are really important to understand the basis. So when it does turf out an answer for you, you can comprehend it. If you just get into the concept where you ask the machine, it gives you something, and you don't appreciate how it works, then surely that's a failing. And because when it does break, how are you ever going to fix it? This is why I'm confused, Dave. You can see the conundrum.
James, Catherine, do you have a perspective?
I love what you said about vocationizing education. I absolutely agree. It's funny you brought up the calculator example, because I thought the same thing. Many of us grew up with teachers saying you're not going to have a calculator in your pocket, and now we have all of the world's information in our pockets, and can look at that at any time. So personally, I need software engineers who can code in Python. So please keep that going for right now, until Jim and I can write all of the software I need for my quantum computer. I'm going to need engineers who can continue doing that. And I like what Rob said. I still need someone who can debug it when the computer writes it incorrectly. But I love what you said. I think we should really be thinking, especially higher education, higher learning, around how to think, how to do problem solving and think critically. And even as someone who stayed in the hard sciences, the liberal arts are what makes us people. That's our culture, that's our background, that's what we've done. I would hate that people aren't reading Shakespeare or Faulkner or the great writers of the past, and just knowing what it's like to be a human, right? It would be great if we could see a shift in the way learning is done, and we're not just going to college to get a job. We're going to college to expand how we think and what we think about, and all of the beauty that's in the world.
Immensely well said. So, Rob, I think we've sorted it out. I think we've cracked that one.
Did we?
I think we did.
Sorry.
I think we did.
Yeah, okay.
I think we did.
It was actually quite a good explanation to say education needs to modernise, but keep the humanity at its core. That's as I summarise it.
First time for everything.
We've fixed one. Fixed one.
Well, we are so glad to have you guys back on. Last time around, we had Catherine and one of Catherine's colleagues, Alex Del Toro Barber. And this time around, of course, we've got James stepping in. And the episode we did last time around with you guys was Quantumania. And we explored very far-reaching ideas of what quantum is and where it might take us as a society and, as organizations. And you guys have had a busy year since then. The release of the Willow chip, which is your latest quantum chip, has sort of come out, and it would be good to maybe start there. So, James, why don't you just give us a bit of context on what's been going on, what Willow is, and we'll jump off from there.
Absolutely, and thank you for having me. So Willow is the latest quantum processor developed by Google Quantumania. It has 105 qubits, and we believe best-in-class performance across many of the common performance benchmarks. We designed Willow specifically, start to finish, with error correction in mind. And we're going to talk a little bit more about what error correction means, but we didn't want to focus on vanity demonstrations with this chip. We really wanted to be pushing further on some of the hardest things in the field, tackling the engineering and the science challenges that are necessary to actually make sure everything's going to work together as we scale up these systems. And error correction really informed many of the aspects of our processes, how we thought about the chip architecture, the gate development, the calibration, the fabrication, each of those pieces, because we wanted this to be our first demonstration of actually doing error correction in an integrated system.
So how close is Willow to like a production ready in the wild system versus like a next stage of R&D, would you say?
Still it was a significant step in R&D, but still a step in R&D where, there's a lot we needed to learn. But, as someone who's been in quantum computing for almost 2 decades, getting to this point where we've actually proven error correction can work on hardware, has been a significant step we've been working towards, for decades, since this was kind of theorized back in the 90s. So being able to actually push towards this, show that we're going to be able to scale these systems in the lab, is a very key step towards actually making it productionable, where we can actually get it out to users and they can start working with it.
Now, physically, kind of in inches or millimeters, how big is it?
Trying to speak to my non-US friends here, I'd say it's probably on the order of 50 millimeters by 50 millimeters. So, about 2 by 2. These quantum chips are still fairly small. Now, obviously, all of the components that go with that, the whole system, it's very large, but the actual quantum chip is still very tiny.
And it's 105 qubits. I think I've got that right. So
correct.
Help us understand what that means in terms of how powerful is that?
Well, so this was our first chip pushing beyond 100 qubits. Obviously, as we talk about use cases and, actually doing real, pushing beyond classical boundaries, we're going to need thousands, millions of these physical qubits. So 105 qubits in the grand scheme, still pretty small. But for us, being able to start incorporating and growing these systems was a key step. So it's pushing on some of the boundaries. We're still able to fabricate these devices on a single wafer. We don't have to worry about things like that. But it was a key piece for us as we can scale larger. So when we talk about these error correction codes, you can think about it that we have to continue increasing the distance or the number of qubits we can connect together. And so by going to 105, we could do a larger distance code, which allowed us to get that better result. And so we want to continue scaling so we can continue running larger and larger codes and continue pushing on how good of a job we can do.
And I'm trying to get a sense of its processing potential. So have you got an example of, say, like a problem that a 1 qubit chip would be able to solve, and what kind of problem you could solve with a 100 qubit chip?
So one of the benchmarks we've been using, even back since our 2019 early quantum supremacy days, is this random circuit sampling, or RCS experiment. And so with that, to be fair, it is a little bit of a contrived example where we've built a benchmark where we wanted to see, could we beat a classical supercomputer at anything? I would love to beat a supercomputer at something that actually impacts our lives, but in these early days we need. That's right. So this 105 qubit device allowed us to perform an experiment in the random circuit sampling better than even the frontier supercomputer that we have here at Oak Ridge National Lab. So we were able to perform a calculation in about 5 minutes that would take 10 septillion years, which is a number that is so outrageous that I have trouble even picturing it. But I mean, if I basically I'm saying we can do a calculation on this 105 qubit chip that would take orders of magnitude longer than the age of the universe on our very most powerful chip. And now I'm sure there are going to be detractors from other companies or other quantum hardware providers who would say, but the whole reason it's faster is because they picked an experiment that of course would run faster on quantum, and they're right. But this same experiment, when we did it in 2019, the great thing is that as quantum chips get better, our classical chips get better as well. And the people writing the algorithms for these classical computers, the computers we use every day, get better. So the demonstration we did in 2019, the classical computers are getting better and better. So they're starting to catch up. So we wanted to show without a doubt, with the Willow chip, you can now do this. That there's no chance that the classical computers are going to catch up anytime soon in that particular area, that very niche area of computing.
Yeah, I mean, I think it's fine that you chose something that would kind of lend itself to that chip, right? Because that's what you're trying to test in the first place. So
exactly,
perfectly valid from my point of view.
I mean, and it's horses for courses, isn't it? With digital and quantum, it'll probably be a fusion somewhere in the future, won't it? So we'll still use digital, and we'll use quantum. So it's what's the best for the thing we need to solve, and we'll mix mode it, or at least that's how I see it. I mean, is that, would you characterize it, or do you see a point where quantum will get to such a level that actually digital would be minimized in the ecosystem?
So that's a very great point. Quantum computers, I am a true believer. I think they're going to change the world. It's going to be amazing. But quantum computers are never going to allow you to watch cat videos or do spreadsheets or do all of the amazing things.
I thought you said they were going to be useful, James.
Unfortunately, we probably won't be doing quantum computer podcasts on the quantum computer. So we're absolutely going to still use our classical and our digital computers. And you nailed it, Rob, that it's the combination between the two. So a quantum computer is not going to be useful unless you have that very powerful classical computer tied to it. So we're going to have to do lots and lots of the computation classically. And actually, our goal is going to be to do as little of the computation on the quantum computer as possible, because even as fast as our devices are, they're still going to be a lot slower than we can do things classically. So as you're having to do a lot of this error corrections, you're having to feed forward the results that you can do the next step of the calculation, you're going to end up having to see these hybrid systems where you're tied back and you're doing lots and lots of classical calculations, a little bit of quantum, and then zoom back to the classical computer.
And you mentioned in your description of the chip, what was notable about it was error correction. So you just want to go into that, the next level down on what is error correction specifically in this case, and why is it such a critical breakthrough?
Absolutely. So as we're building these systems, and you mentioned that the Willow chip has 105 qubits. Those are 105 noisy physical qubits. They're actually the qubits that we've patterned onto the chip in our fabrication processes. And what we did with the Willow chip was we tried to design, or we were working to make a single logical qubit. And so with a logical qubit, what you've done is you've encoded all of those physical qubits into a single protected qubit that we refer to as that logical qubit. And so in classical computing, in the computers we're using right now, our laptops, the errors in those little transistors are very, very small. So we might have one error in 10 to the 15 operations. And so you're not going to see, you don't need the error correction there. We have it underneath to kind of protect the memory, protect the way we're storing the data. Because my quantum computer chip, the qubits that are inside of that are so noisy, we see an error roughly one every 1,000 operations. And so if I need to run 100 million calculations, but I'm going to have an error every 1,000 calculations, what we're trying to do is we're trying to encode all those physical qubits, protect it so that we are correcting those errors as they occur so that it doesn't break down my computer as I'm trying to run a calculation. So what quantum error correction, a simple way to think about error correction is, can I use lots and lots of noisy qubits that have reached a certain level, this threshold that I was talking about, where as I add more qubits, the error actually gets better. So up until we had the Willow demonstration, as I tried adding more qubits to do my error correction, the errors were getting worse. So I wasn't seeing any benefit from quantum error correction because my noise had not reached a level where we could actually correct for it. But with Willow, for the first time ever, as we scaled the system bigger, as we went to larger and larger grids of these noisy physical qubits, we were able to actually decrease the errors exponentially as the system got bigger. And so that was the key result. Is you're now seeing we've gone below this threshold that mathematicians and computer scientists had described years and years ago. Of now we're finally seeing the benefits. We're finally able to take advantage of that error correction.
So, Catherine, before we go on to talk about some use cases and the potential impacts of where we're up to, just cast out a little bit for us. What's the next steps in design and development?
So the next hardware, or perhaps rather a system milestone that we're working towards, is what we call a long-lived logical qubit. James just mentioned how we encode a logical qubit, but this long-lived logical qubit is really one abstract, nearly perfect quantum bit. And actually, it's interesting. You're starting to hear companies across the quantum industry speak of building logical qubits more and more often now. In fact, I was at a conference this week here in London where people from 2 companies proclaimed they have tens of logical qubits. So I guess in that context, people might wonder why our grand goal is to build just one logical qubit and why this milestone is so important and represents meaningful progress for the field. And the answer is that for this milestone, we define our logical qubit quite ambitiously. Essentially, we define it to be the unit of computing that you will need to be able to run a fault-tolerant algorithm on a quantum computer. And most commercially valuable algorithms are expected to be in the fault-tolerant regime. So it needs to have fewer than 1 error per million computational steps. So yes, that's the big next hardware milestone. Of course, there's also lots of cool work in flight in algorithm development. And in fact, also at the point where hardware and application development efforts meet. So we can talk a little bit about that as well, if that's interesting.
Yeah, why not? And give us a sense of some time frames as you're describing these things. How close are we to that million mark, for example?
So you mean to the mark where we have 1 error per million computational steps?
It. Yeah.
Or a million qubits, or a million logical qubits, which I would find great coming from the theory side. So I'm afraid we'll have to tell people to stay tuned.
Right, gotcha.
For the logical qubit, the long-lived logical qubit. Gotcha.
Well, let's go on to then use case and impact, James. So these things in the wild and in the real world, where are we up to in terms of them being leveraged? And what do you think the major impacts are going to be?
No, absolutely. So, I think it's been great over the last couple of years seeing more and more quantum systems coming online, because we've got a lot of, and I mean across the industry, there are a lot of very smart people, both at Google and other places working on applications. But I think the key step is building the sandbox, making a place where we can bring in the community to think about some of these use cases. And, as we make our systems available, more people get access. I think they're going to come up with new and exciting ways to use it. I think about it kind of like an app store, right? Like if I build the app store, then smart people will come in and they can build useful apps for it. Not just us physicists trying to dream it up, but what might come from that. Because we all have our inherent biases. I come from the science world. Most of what I think about is how we can use quantum computers for physical demonstrations, right? How we can better understand simulating physical systems. That's kind of what got everyone started building quantum computers. So how can we better understand how molecules work, how they interact, these different processes? And from there, there's great optimism that we're going to get, by understanding these fundamental aspects of chemistry and physics, we're going to be able to discover new medicines. We're going to design more efficient, batteries for electric vehicles, accelerate progress in fusion and new energy alternatives. And so that's where a lot of our focus has been internally with our theory teams and our application teams, thinking about, as Catherine mentioned, these future fault tolerant systems where I'm not working with noisy qubits, but instead I have perfect qubits, and I can actually simulate nature at a level that we can't do today or maybe ever. But we're also, I'm still very hopeful that we may be able to see some beyond classical applications in this noisy era we're in. There was a lot of excitement built kind of in the 2018 timeframe when we first started getting systems online that maybe we could do something with noisy qubits, and there's still hope there. Our team is still pushing on that, especially as these systems are scaling up in size. But as Catherine mentioned it, and I think our key point is, it's probably going to need to be an error-corrected system. Hopefully, it doesn't have to be a million qubit error-corrected system. But I think at Google, we're optimistic. We're going to see something in the next 5 years that actually is transforming and is actually impacting the lives of people with the system we're building right now.
Well, one of the things when you go there, which I love about quantum, is all the use cases you talked about there were essentially future of humanity, like better power, understanding molecules,
Did you cry
creating
a bit
better medicine.
Humanity?
I know, David. It's emotional for you, but it's one of those things. It's like great
humanity.
hope when you talk about it. It's all the things that we need. It's like this massive work towards it all is like paints this really bright, happy future, and I quite like that because often we'll get into the dystopian end of breaking up down emotional. It's that thing which I think it's deeply positive. Yeah. It's deeply positive, David. That's what you've got to look at. So I think it's worthy that because it's all for the greater good, which I quite like.
Yeah, and what's exciting actually is that a lot of these examples you just mentioned are in the kind of quantum simulation domain, which is in fact where many of us expect the first wave of sort of major societal and commercial impact to happen. So, just in case there are some people listening for whom quantum space is a bit less top of mind. This is where you use a quantum computer to simulate and analyze a natural system. And being able to do this well unlocks all this great potential for progress in the development of medicines, batteries, materials required in industrial processes, the design of fusion reactors. And there's actually some really cool development there. Even within our team, we have an algorithms and applications research team that works loads on quantum simulation. So yes, for the algorithm enthusiasts, definitely go and hit the archive and look up our most recent paper on quantum simulation with sum of squares, spectral amplification. Because, it really speeds up algorithms hugely.
One area that's, close to our heart that we haven't mentioned is there also is going to be pretty big impact, we think, with AI. So I'll be honest. When I first heard this coming out, maybe a year or so ago, the fusion of quantum and AI, I thought, man, what other buzzwords can people cram in there? Right?
It's all in one. You shove it all into one sentence. Yeah.
Exactly. How quantum and AI didn't make sense to me as someone working on the quantum computing side of the world. I was like, well, AI is taking data that exists and building these amazing models. On the quantum side, I'm trying to solve these future of humanity, physics problems. How could that possibly be? But recently, and especially since I've come to Google and I've seen, some of this merger between the two, or the intersection, I do think that could be a very interesting place to play, and that's something I'm excited to see what we're going to come up with.
I want to say that out loud, actually, because we're still in the midst of, are we going to use video with our podcast or not? But you can actually see you are glowing, both of you, talking about this topic. That's about quantum. For me, it feels quite theoretical, and I have no clue what we're heading towards. But the enthusiasm is very It also makes me hopeful.
Infectious.
Yeah.
I really have to agree that quantum and AI is a really interesting space of intersection. There are lots of cool touch points, and they're really complementary technologies. And it's funny to see that we're kind of coming at this from so many different angles, because there's AI for quantum, all about how can we use AI methods in our efforts to build quantum computers, but also quantum for AI. So, how can quantum chips be used to somehow accelerate AI? And then also, I guess, the kind of purest interpretation of quantum AI, where you're actually doing machine learning on a quantum computer. And we're seeing really cool progress in all three of these areas at the moment.
I was going to go on to the the nexus point of quantum and AI and what that's going to mean from an AI perspective. So there's obviously in the world of AI, there's lots of talk about the speed of innovation, where it's going. It does impressive things today, and it will probably be even more impressive in 12 months' time. But in your heads, as you're thinking about this, what is applying quantum to AI actually going to do from an AI perspective?
So applying quantum to AI, there will be no doubt many ways in which we will do this, but some of the early ways in which we've discovered this should be possible is, for example, providing classical models with data from quantum computers, which in some cases can really change the computational complexity of your problem. Wow. So this is kind of powering classical AI models with quantum data. Another cool example is for some distributed models, it's been shown that it's possible to achieve exponential reductions in classical data transfer if you have a small quantum computer in the loop. So you could see this as kind of sending qubits between different parts of your classical compute infrastructure, allowing you to do inference much faster.
And when you boil it down and compare it to digital on a power level, is there a parity with the amount of energy required to process quantum, or is there a big difference? Because we're talking about huge computational leaps, but does that come with a massive power? Obviously, if I had to run the digital computer for septillion years, that's a lot of power needed, more power in the universe. But is there a parity, and as they're operating, the amount of energy they need is similar or not? I suppose it's an area
Well, in this quantum for AI case, that is certainly what you would be looking at, because if you are trying to achieve this exponential reduction in classical data transfer, or you're trying to really reduce the computational complexity, then you are basically reducing the compute that's required in the first place to learn. That is a kind of a very exciting area of development. But more generally, if you think about doing quantum machine learning, doing machine learning on a quantum computer, there, if you think about quantum data, so you will probably have heard about lots of different sensors being developed across industries at the moment to measure things, from imaging sensors used in hospitals or brain scans to chemical sensors which rely on spectroscopy, etc. And you can imagine that a quantum computer it's a really native task for a quantum computer to learn from this kind of data. Whereas if you try to represent that on a classical computer, you would need a huge amount of memory.
As you think about digital, it's really an efficient way to process information because we boil everything down to ones and zeros, process it, and then boil it back up to an image or an audio or something that the human comprehends. With quantum, it processes on a much more, it's a completely different level, isn't it? And so I suppose that helps as well. But it's always interesting for the listeners to understand that sort of difference in how it actually operates and is able to do so much more with such smaller amount of resources available to it.
Yes, exactly. And there's so many exciting ways to leverage that are sort of constantly emerging from the research field, sort of hot off the press. So maybe as another example, quantum computers could train certain neural networks exponentially faster than classical algorithms when the data follows natural patterns, like, let's say, Gaussian distributions. So this is even for cases where the distribution is provably hard in the complexity theory sense to learn with, using the standard classical, gradient-based algorithms that people rely on a lot.
Does the introduction of quantum into the world of AI move us faster towards AGI, do you think? Or are they not connected in that way?
I would actually say that the introduction of AI into quantum moves us faster to building quantum computers, because we use, so many AI methods in our hardware development effort. Many people will have maybe seen the Alpha Qubit paper, which we came out with a partner team in Google DeepMind. And, James has talked about error correction a lot. And decoders are what, in the error correction loop, is what identifies the errors in the chip. And so what they did is they built this decoder, which is a recurrent transformer-based neural network that learned to decode the surface code really well. And this is just one example. We do this really across the team more and more.
Amazing. James, I want to talk, trying to get my head around the nature of the deployment of quantum going forward. We've talked a bit about how it's likely to be some form of hybrid with digital. But does that mean that quantum is going to be a fairly niche technology, or is there a point where it can be deployed more broadly?
Absolutely. So I think in the early days, we're going to probably see it be much more niche, where we're going to make these systems available over the cloud, and we're going to allow you to tie your quantum workload into a classical workload, and we're trying to make that as seamless as possible. But I do think these we're going to be able to solve all of these problems that classical computers can't solve. But like I mentioned, the areas right now that we've identified where that advantage is, those are still pretty narrow. And I think at least in those early years of fault-tolerant systems, we're going to see very niche deployment where quantum computers are used in just a very small area where we can actually see value. Also, these systems are going to be, it's going to be very much like the early days of classical computing, where they take up entire buildings.
Right.
They cost a ton of money to build, and so then they cost a ton of money to access. And so in my mind right now, I'm seeing it very, very niche. But then I think about, reading books about those early days of classical computers where, someone's saying, oh, we're only going to build 5. And
We'll only need 3. We don't need more than 3.
No one will ever. Yeah. And so I'm sitting here going, the voices of the past are echoing in my head saying, you're so narrow-minded, you can't see the future. And I love to think about a world where we're using it for all kinds of other things, but I think in those early days, as we're kind of figuring out what we're using these systems for, it's going to be niche, and I'm going to try and make them available to as many people as I can. But right now, I'm questioning how wide that adoption is going to be, and but honestly, I'm just really excited to build these systems. That I'm a hardware guy. I want to build a quantum computer. I want to get it onto the net, and I want to get as many people accessing it as possible, so we can start finding the use cases that I'm just not creative enough to come up with. So that we can, same as the folks building these back in the 50s and 60s who never would have thought of, cell phones or AI or any of those applications that we've come up with. So. I would love to be able to go 100 years in the future and look back and laugh at myself at how I was, not able to be creative. But my cynical position right now is, narrow to start, dreams of big, wide adoption. But even if it is narrow, even if we're only curing cancer and developing new drugs and new energy technologies, I think, that's still quite the success.
Pretty good.
So we'll take it.
But it's that... It's that thing, though, when you talk about the people who predicted, we'll need 7 computers in the future, they stood on a podium and said it with absolute and total confidence, which is always the hubris, isn't it? That says it. What you've just said there is it's probably going to be quite widespread, but I'm not sure. So, we'll see what happens. That's a much better way to say it than the confidence of the past that just... the failure of imagination to see where it was going to go. So, I'm with you. We should look backwards and go, it's probably going to be everywhere, but we don't quite know how. And then when you think about it's available to me as a consumer and I can go and get hold of quantum capability, what's that mean from a commercial aspect and sort of people using it for commercial gain or applications that then become saleable, etc.? I mean, where's the return on that? Because that'll start a whole new flywheel process off where we go from research to commercialization, and that'll create a massive lift. I mean, what's your view on that and when that might occur and how it might happen?
So what we're looking at here is really the point where hardware and applications development efforts meet. I think the field has for a long time been trying to break through what you can, in a way, think of as the ROI frontier. We tend to call this the beyond classical computations frontier. Some people call it the sort of quantum advantage frontier. But this is where someone uses a quantum computer in the here and now to do some commercially relevant computational task, which is actually intractable on classical computers. So this is where you can conceptually, at least, in a first flight sense of the term, begin to benefit commercially from being a user of quantum hardware. Because we have quantum computers today, which in terms of raw computational power, and James talked about the RCS benchmark, which is a great way of measuring, the kind of raw compute power of a quantum chip. And so in terms of this benchmark, we have quantum computers which can outperform classical computers to a really impressive degree. And we also have algorithms research results already, which point us to where we can get commercial value out of using quantum computers. But those tend to be for quantum computers of the future. They need to be fault tolerant. They need to be really much larger than what we have now. And what we haven't quite seen yet is a publication of a result where someone actually performs a proof of concept computation on a real quantum computer, which is beyond classical. But this is an active area of research that I think is moving fast and is a space to watch.
I wanted to ask quickly, actually, about, I think one of the scaling challenges, if I understand it, is to do with the cooling issue and the refrigeration. I wondered where you guys are up to with that, and did Willow have any breakthroughs in terms of the level of cooling that it needed, and how you think you're going to crack that problem? Because that to me feels like that's the issue with computers as big as rooms, isn't it? A lot of it is to do with the cooling systems.
So we certainly had to scale up the fridges in the context of scaling up the chip. I think that will continue to be the case. There are challenges on every level of the stack to solve when you are moving on to the next generation of hardware. But it's true that the cryostats, so these big refrigerators that quantum chips live in, are a very expensive component of the hardware stack,
right,
and are challenging to scale. So we work with our supply chain partners sort of in a co-development R&D setup. And as we map out future chips, we need to also map out sort of future versions of this refrigerator and figure out, for example, are we going to build one huge refrigerator, or are we going to try to, have interconnects and have a more modular approach? And I think that from a sort of research and engineering perspective, the answer really has not been found yet as to how we're going to do this when we get to a very large scale. But at least we managed for the Willow chip.
Yeah,
and coming at it from a physicist standpoint, and I know it sometimes frustrates our engineers here, but in my head now I see some of these scaling problems, we're now able to push them off, and I can think of them as engineering problems. And so when they were physics problems, I was worried we might not ever be able to solve them. Okay. But now that they're engineering problems, I have so much faith in our engineering team. I think, well, of course they'll figure that out. They'll figure out a way to get the cooling where it needs to be, or the different connections and the wires where they need to be. So that's been a great thing here is seeing that some of these impossible physics challenges, we figured out how to solve those. And now it's just the listeners can't see my air quotes, but it's just an engineering challenge that I feel very confident we'll be able to solve.
I love that. You just go, so we've fixed the theory. Just go and build it now, chaps. Off you
exactly.
go. Have fun.
Easy.
Enjoy. Let me know when you come back and it's working. And some engineers just steam pouring out of his ears, going, "Oh my words, yes. How are we going to do that?" But anyway, yes,
I guess while we're on kind of fixing future problems, Catherine, let's talk a little bit about investment and effort. So, how does all of that work? And kind of how do you apply it in a way that kind of takes you forward in a dial moving way? I would imagine the amount of problems that you're trying to work through and think about, so many of them might end up being nugatory. So how are you pacing your way through that?
I would say that while we are in this R&D sprint where we have, a small closed group of expert users rather than a product with huge numbers of users in the general public, we can be quite focused in our investment on the hardware development to get it as quickly as possible to a place where the hardware is able to accommodate the kinds of applications which the user will really see an ROI from. But of course, we besides that also invest in applications and algorithms development. We have a great team working on that. And indeed, when you think about hardware development, that is really sort of system development that actually requires a lot of software engineering as well. Because the quantum stack consists of a lot of hardware and software layers. And then on top of that, there's the product development. This is defining the gap between achieving a full system performance milestone and actually being able to make that useful to the world in the form of a compute capability and doing all the engineering work to close that gap. And then maybe finally, I guess it's people and the broader ecosystem in this really emerging field. It's very important to do, I guess, workforce development and engage with the broader ecosystem.
Well, while we're still future gazing, and maybe just to bring the conversation to a close for at least this year and revisiting it this year, one of the things that always strikes me when we talk to you guys is you generally drop a couple of mind-blowing quotes like the one that you did at the beginning, James, around how much faster the chip was working than a traditional computer. I wonder, like, as you're going through the work that you're doing, have you got a favorite one of those, like a factoid about what quantum has achieved that surpassed your expectations or got to some crazy number like the one that you just described earlier? Feel free to have a go at that in any order.
I think my favorite quantum quote, I do love the fact that we're able to perform some of these calculations so much faster than any supercomputer. Of course, those are very fun. Yeah. But honestly, my favorite quantum quotes, go back to Richard Feynman, the person who first kind of theorized quantum computers. And, it was, if you're going to try and simulate nature, then, the computer needs to be physical, right? We need to build, if you're going to try and simulate a quantum system, the computer needs to be quantum. And what an amazing problem this is to try and solve. So though it doesn't have to do with the metrics so much and on our quantum systems here at Google, just some of Feynman's wisdom when it comes to the complexity of this problem and how fun it is to go after solving those very hard problems. Esmee was mentioning glowing. It's true. This is my favorite thing. I don't tell the bosses, but I might do this for free. I just love working on quantum computing so much. So,
don't tell. No.
That's my favorite thing is, this, Rob, you mentioned it too. Like the amount that this could impact the world, that's what gets me up out of bed every morning. It's just that this could be the key technology of the century, right? That this could change mankind. And so, while it's not so much a technical thing, that's really what gets me so excited. And also just thinking about how insane it is that quantum mechanics is real and that this is something that actually works. Because even now, 20 years of thinking about it, it doesn't always make sense in my head. And so, the fact that the more you think about quantum mechanics, the less you actually understand. The quotes like that, those are the ones that have always stuck with me.
Yeah, wonderful. Catherine?
I think perhaps the one that I find the most mind-blowing is what will it mean for us to be able to create a kind of digital twin of our own brains, and where will that take society, and what does it mean even for the human condition?
Ez, what's on your mind?
Yeah, I think it's something that we've already been touching upon throughout this conversation already, talking about a fixed mindset with we only need 7 computers. But if you talk about quantum, and we just mentioned that we don't know all possibilities yet, and we might even, looking into the future, we might be entering an era that we will never have all opportunities or possibilities in our heads, because it's way above our head, actually. So if you look into engineers and product managers, they've been shaped by deterministic thinking. You write code, you run it. If it breaks, you debug it. You trace it back to a root cause. But quantum computing forces us into a different reality, right? So not one outcome, but probability space, not certainty, but potential. And I recently read a piece in Harvard Business Review on teaching teams to think in probabilities. And that made me wonder, quantum isn't just a technological leap, it's a mind shift. So how do you build and lead teams around that? How do you onboard people into a world where answers are rarely final and logic is non-binary? And maybe even broader, does quantum also demand a new kind of leadership? One that embraces ambiguity and works with complexity rather than trying to control it. What's your thought on that?
So my job, I have to understand digital and digital systems, how they operate to be able to deploy them, right? And I still read up on quantum and it still makes my brain hurt. So I do think there's going to have to be a mindset shift, like you say, that says I'm going to have to think differently about the way you think about solving problems. And that'll be a big leap for loads and loads of people. So when we talked about the commercialization in the previous part, to get the commercialization working, it's going to be very clever people who think differently who are going to get there first, isn't it, in the community? Because the traditional sort of digital thinking need not apply from my perspective.
I absolutely agree. I do think it's a little bit of a mindset shift. I think, it's frustrating for those of us on the product side because we can't look at this like we do our normal products. It's very hard to think I'm engineering towards something where I can create the use case. I can't start with the customer necessarily right now and work backwards because I'm still laying the track as my train is going down, and so I think it is requiring a little bit of a shift in who our leaders are. They have to have patience because they have to understand we're still figuring a lot of this out, and that can be tough. We have a lot of very energetic folks leading these quantum companies, and so they have to have the patience of let's make sure we do this right. Let's make sure we're not overselling where the systems are today, because I think the global community is going to look and say, quantum computers have been 10 years away for the last 30 years. So when are you guys going to actually deliver something? And then at the same time, if that fatigue sets in, or if we're not able to meet what we've been saying we were going to do, I worry that how does that change investments, especially as things like AI and other things are out there. They're sexy things to invest in. So we have to be careful. We have to have patience, but we also have to push just enough that you have that little bit of heartburn that makes it tough to go to sleep at night, because we can't relax too much. So we have to continue pushing ourselves while having that patience to kind of, I think it's a little bit of a shift from how tech is normally done, just because we're not sure where this is going to go and we're not sure what it's going to look like. But it has so much promise that we can't stop. So we have to keep running, but also keep our eyes open so we don't run into any trees.
Yeah, absolutely agree. And perhaps this is something that you see more broadly in other areas of deep tech. Personally, I think if I was not working on quantum computing, I would probably be working on space in some way or other.
Right,
and I imagine that the people working on space have precisely these same challenges, where there's just huge uncertainties. You need to kind of de-risk the science, de-risk the engineering, do a lot of scenario planning in a pretty meaningful way, where it can be that you have to do a huge pivot on your technical architecture if something scientifically is discovered that you maybe were not expecting. Perhaps in a more literal sense, though, about your regarding your question, where does this probabilistic nature of quantum computers affect our teams in reality, and how do they cope with it? I find it interesting to see that at this stage, it's really not only the people building the chip and the software which calibrates the chip and does the error correction that need to think about noise, but it's actually also the end users. So the applications developers at the moment, to be able to get anything useful out of the quantum chip, need to really think about the noise, the probabilistic nature of the chip. And if they don't, then it's not really possible to make it work for you and usefully do something on it.
To come at it maybe from a slightly different angle, and on your last point, as where you were talking about increasing complexity and dealing with ambiguity and forms of leadership. I mean, it's a good provocation. I think leadership in its truest sense is dealing with complexity of human systems anyway, right? And I'm not sure what the quantum effect is going to be on that. So, I guess the way I would try and parse the question is, if leadership is dealing with human systems and you put quantum into a human system, does that fundamentally change the nature of how the human system then operates? Because I think as the world has gotten faster and faster and faster and less knowable as we've gone forward, leadership has had to deal with increasing complexity anyway, hasn't it? Like you look at something like the Cynefin framework, where it talks about moving from a sort of a complicated world into a complex world, and in a complicated world, it was very noble. You could maybe do a strategy that would be 5 years out. Now, if you did a strategy that was 18 months out, you're probably stretching what's predictably possible.
I think we're even further than that now, right? It's the same as what we said with the 7 computers. I don't think our brains can wrap around the type of complexity that we're heading towards.
I think you're right. I think what that reminds me of is, that there's a statistic about the human brain can only handle knowing something like 75 people or something like that. And, evolutionary, we've grown up in sort of villages, and then villages became cities. And then you were tracking news just through traditional networks and newspapers of what's going on a global level. Because social media then has now made that real time and practically instant. And you can see the impact that social media has on the human brain, can't you? So I think you're right. I think we are in that world of absurd complexity already. I have no idea what quantum's going to do. Catherine?
Is this distinction between complicated and complex, I've always found quite a fascinating one, because I think quite literally complicated means that there might be many interacting parts, but actually the system is still predictable.
Yes, that's
Whereas
right.
a complex system, there you are dealing with something that becomes very hard to predict over time. And so in a sense, what we need is to be really nimble and to adjust our strategy and the way we sort of move the effort and the teams forward as we go along.
I think there's a fair bit of AI helping us with complexity as well. We already use it in basic tasks to solve complex issues and advance us faster. So I think there'll be some fusion of human thinking and artificial thinking to remove complexity from the system. So we'll learn to use the tools at hand to make it easier for us to cope. But you're right, you get to cognitive overload occurs quite frequently in certain systems, and we know it can be very damaging. So I think it's the advance of tooling around us that we use to deal with it maybe is part of the answer, not the full answer though. You still have to understand how the system works at the basis level to be able to fix it when it breaks.
Good provocation, Ez. Lots to think about in that. Now, before we move on, I actually want to ask you a little bit of a wildcard question before we wrap up today.
Run for the hills, everyone. Run for the hills.
My connection is dropping.
What? Dave, you're breaking up.
Now, does the nexus of quantum and AI make the possibility of us living in a simulation greater or lesser?
What, you're asking for a vote?
I'm asking for a point of view. Well, I know what your vote's going to be, Rob, but don't show your.
We already live in a simulation. I'm convinced.
Sorry. Don't show your hand.
It's a funny thing to ask because we recently had an offsite and towards the end of the night, this question did come up, and we had a couple of people pushing different ways, and we're kind of talking over it, and then one of our more senior scientists who is very well respected, very intelligent guy, stands up and goes, you're all idiots, we're not living in a simulation, and stormed off to bed. So
emotions ran high.
Emotions definitely ran high, but I respect him a lot. So it's a fun thought problem, and I like to think about, but knowing his standpoint, I thought, well, maybe that must be the answer. He's a smart guy, but it is an interesting thing, right? I talked about quantum physics even existing, and thinking about that we have these physical constants that are constant across the entire universe. Sometimes that makes me think like, it certainly seems like something I'd program into a video game or a computer simulation where, you can never go faster than the speed of light. good, that'll send that one. And then
it's convenient, isn't it? Things like that are convenient. If you own a simulation, you go, these constants can't be broken.
These are the unchangeable things. So it is certainly a fun problem to think about.
And in the main conversation there, Catherine was talking about digital twin of the brain and needing a quantum computer to be able to simulate the brain. So, so simulation as an idea is something we're developing, right, Catherine? We are thinking about that.
I don't think I back myself to predict 5,000 years into the future.
No.
Go on, give it a go. Nobody's going to be around who hears it, so you'll be fine. Just make it up. It's good.
But my general rule, being I would say realist optimist, is that as long as I can see some sort of plausible-ish technical path towards doing something, I can believe it.
Right.
And simulating the brain, I feel like is something that I can see how I would do that. I feel like I can draw a diagram that would sort of represent an approach to doing that. Whereas simulating the universe, that I'm not sure I quite see sort of a technical, critical path to doing. And I feel like actually what we're getting into there is questions about religion, which maybe are not quite the types of philosophical questions you guys want to discuss.
We'll take it. We'll take it.
Yes, I would put my philosopher's hat on if I would think about that topic rather than my quantum computing hat.
Well, very nicely summarized, and let's leave the conversation there for today. A huge thank you, as always, to James and Catherine, who just bring such fascinating subject matter to the conversation. So, guys, great to see you, and thank you very much.
Thank you so much for having us.
Thank you.
Now, we end every episode of this podcast by asking our guests what they're excited about doing next, and that could be simulating the human brain, or that could be something in your personal life that you're looking forward to doing this weekend. So, Catherine, why don't you kick us off? What are you excited about doing next?
Well, it's extraordinarily sunny here in London, so I feel like that is unusual enough that it must be mentioned, and I'll have to go and seize the day tomorrow. But besides that, I'm just so excited about the long-term product roadmap. I think we have some really great ideas for how we can make these quantum computers useful and available to the world, and what the sort of main milestones there should be. So, yeah. James, I hope you're looking forward to building all of those versions of the product too.
Absolutely. So, we're starting to have our very first external users running on our quantum hardware. So that's something I'm very excited about. But more short term is, Google I/O is coming up next week. So I'm heading up to the mothership in Mountain View and excited to see some of the things that are going to be announced there. So that's top of mind for me right now. But yes, getting users on hardware, that's what is keeping me going right now.
If you would like to discuss any of the issues on this week's show and how they might impact you and your business, please get in touch with us at cloudrealities@capgemini.com. We're all on LinkedIn. We'd love to hear from you, so feel free to connect and DM if you have any questions for the show to tackle. And of course, please rate and subscribe to our podcast. It really helps us improve the show. A huge thanks to Catherine and James. Our sound and editing wizards Ben and Louis, our producer Marcel, and of course to all our listeners. See you in another reality next week.